Good afternoon, everyone. I'm Vamshi Allah, and today I would like to share with you how we tackled one of the toughest problems in telecom, detecting billing anomalies without depending on the label data. Our approach combines cutting-edge self-supervised learning and expansibility to improve accuracy, reduce operational cost, and build trust among telecom operators. Here is the problem scope and outcomes. Let me start with the story. Imagine being a telecom operator and getting daily complaints from customers about overcharges or discovering revenue loss due to missed charges. Existing systems depend heavily on the labeled data, but in telecom billing, labeled anomalies are rare and expensive to collect. Our mission was simple: learn billing patterns from normal unlabeled data, reduce false positives that burden manual review teams, and provide expansible results operators can trust. The outcome we achieved of weapon score is 0.91 and AUC of 0.94 with reduced false positives by 28%, 28%, which directly translate into the lower cost. Coming to the key, what are the key advantages? Here is few of the key advantages. To put in this perspective, think of it as giving operators a smarter self-learning detective, self-supervised learning. It trains itself on the normal billing patterns, no need of costly labeled anomalies. Come to next is advantages: reduce false positives, 28% fewer alarms means teams spend less time manually investigating. And coming to superior performance, outperforms the traditional autoencoders with the state-of-the-art metrics. And the next one is enhanced expansibility. SHAP tells that why a transaction was flagged and making it compliant with the regulatory needs. Let me go into this. This is a simple technical architecture. Now, how does this detective work? First one is contextual learning, like teaching the model to spot subtle differences, similar to how we recognize a friend's face even in a crowd. Next, going to the next component is autoencoder reconstruction. Learns what normal looks like and flags deviations. The other next component is hybrid scoring. Combines outlines distance with reconstructions error for stability. And the next component is SHAP analysis. Opens the black box by explaining which features triggered the anomaly. Where you see here in the left hand side, it's if you're giving telecom billing data, the constructive learning take the one of the frameworks, SimCLR style framework, and it's giving to the feature embedding 128 dimensional, and it's giving back to the reconstructions, which is autoencode reconstruction, and coming to the hybrid scoring, and it's going to the SHAP analysis for feature contribution ranking. This is a technical architecture for this one. Next one is implementation details. Under the hood, we built a lightweight, yet powerful encoder with the 2 dense layers and 128 dimensional embeddings. We tried with NT-extend for constructive learning and MSE for reconstruction, weighted combination of optimal performance. And the train used Autumn Optimizer, a basis of 256 over 100, 50 to 100 epochs, designed to scale for enterprise level data. Next, coming to the performance, how the performance results. Our approach was tested on the synthetic data. Across all the benchmarks, we achieved this score. This is the score. We achieved F1 score and FER, and this is the SSL based metrics. As you see here in the labeled apparent SSL is this one. This is the color and autoencoder baseline color. Which you see here, the SSL is giving the performance in the synthetic data. We'll go into the next one is key anomaly drivers. These are the, let's talk about what drivers these anomalies, and SHAP analysis revealed these three major things. The first one is unused billing rates, unexpected charge or price deviations. And the next one is inconsistent session times, abnormal usage patterns or durations. And the next one is transaction gaps. Irregular spacing between billing events. Interestingly, these three alone explain why the 70% of the detected anomalies, which makes operators' investigations highly targeted. Next, going to the performance comparison. When compared to traditional methods like auto encoders or isolation forest or our hybrid SSL framework, consistently delivered higher accuracy and stability, with significantly lower false positives. It's not just better but it's operationally efficient. As you see here in the SSL model is giving F1 score is 0.91, AUC is 0.91. That false FPR rate is false positive rate is 0.11 or when compared to the other more traditional methods or isolation forest and support vector mission and autoencoder. These are the future research directions. We are just scratching the surface. Our framework includes the streaming implementation and the real-time detection for live billing events, uh, federated SSL learning, training models across telecom operators while preserving privacy, multimodal. Next, coming to the multimodal integration, adding call logs and text just text tickets and network events. The next one is temporal sensitivity, capturing the seasonal patterns and recurring anomalies. Going to this conclusion, to conclude, this framework brings measurable business impact. 28% of the reduced false positives, and the state of art accuracy is F1 score is 0.91. Completely label free, faster deployment and adaptability. This is not just a solution, but it's enterprise level and scalable for global telecoms. Yeah, thank you.